Well, hello, people. My bed is as clean as always, and we are looking at Introduction to T-Tests in Psychology. Now, until now, when we were looking at statistics, what we had was a great thing. What was it? It was the fact that we knew the population parameters. However, in real life, we're not that lucky. Therefore, we often have to just, guess or estimate the population parameters. And the way we do it is basically by dividing the data that we find with n minus 1 instead of, what is it? Just n. But we will get to that. Now, in psychological research, investigators often possess sample data but lack direct information about populations. Most notably, the population variance is frequently unknown. Because the variance is unknown, earlier testing procedures such as z-test cannot be used directly. Now, the most important metric that we have at hand is the variance, because using that variance, we calculate our standard scores. Standard scores here referring to z-scores, t-scores, f-scores, whatever you want to call them. But without the variance, we can't really do much. So we have to estimate it. To solve this, researchers used t-tests. The basic principles of this test were developed by William S. Gosset, etc., etc., etc. If the population variance is known, use a z-test. But if the population variance is not known, we use a t-test. Now we will look at a one-sample t-test. The goal of this operation is to compare a single sample mean with a known population mean when the population variance is unknown. This introduces two new features to the hypothesis testing procedures. Now, because our population variance is unknown, it must be estimated, as we said before. The comparison distribution is not an exact normal distribution, but rather a t-distribution. Now, if I am able to zoom in a little bit here, I would like to show the subtle difference, which I guess I cannot. Wow, this sucks so much. Is it no, the GTA is getting in the way. Okay. Well, I guess we're gonna have to make do with what we have for now, at least. Or let me just pop this here. Yeah, that makes much more sense. So you see, the red lines are our t-distribution. You see how it's kind of thicker on the tails? It's because it's lacking some of the nuances that the population has. It has less extreme values, or rather more extreme values. But as you can see, the red one is with a degree of freedom of 3, and the green one is with 10. As you can see, as we increase our sample size, we get closer to a normal standard distribution, the bell curve. Let me reset the screen. So let's take an example of weekly study time. Let's suppose a college has a known average study time of 17 hours a week. Our mu, or the population mean, is 17 in this case. A sample of 16 students is drawn from a dormitory, and our sample size is 16. Our mean is 17, and our sample size is 16. And the average study time is found to be 21 hours a week. So the mean of this sample is 21. The research question is whether this 4-hour observed difference means dormitory students genuinely study more, or if the sample study consisted of unusually studious people just by chance. Now, of course, as with each of the procedures that we do, we have to look at the standard deviation, we have to look at the mean, we have to look at the variance of the dataset to have an understanding of this subject. Now, I've created this simple steps for calculating anything basically that we're going to learn. So the first step is always finding the sample mean. We calculate the average of our sample scores or the average difference for our different scores for a dependent test, which we will get to, but we are going off of a single sample for now. We will return here, but for now, we just have to look at this. We know how to calculate the mean by now. We're all adults. We all know how to do it. We just take all of the individual scores and then we sum them up. This sigma says sum all of the x, which is individuals, and divide by n, which is the samples. Then we estimate our population variance. Because the true population variance, or the sigma 2, or the standard deviation squared, is unknown, we use sample data to estimate it. We calculate the sum of squares, which is calculated by, x minus m squared. Oh, I don't know why it doesn't say the open version of this, but we calculate the sum of squares and divide it by the degrees of freedom, which is n minus 1. So why is our degree of freedom different? Degree of freedom indicate the number of scores in a sample that are free to vary. Now, the underlying logic between this is, let's say you have 5 data points in your dataset, and then you get the mean of these 5 numbers. So you have the mean just noted down somewhere. Let's say the mean is 5. Okay. So you have the result of the operation, and let's say you have 4 numbers. You would already know the last number because you know the result of the operation. You can just divide by the sum of the remaining 4 numbers to get to the last number. Because of this, we are saying that the last number in that dataset is unable to vary. It's definite. So we say that it's contributing noise to the system, and we want to take it out of our calculation, because if we use it, then we will be just using the same things for the same things. I don't know if I was able to explain it well. I probably wasn't. It's hard to understand. Even me, I don't understand that well, which is quite apparent in my opinion. So just look at how much difference there is. So this graph we're looking at is the estimate variance upon the average of 20,000 trials. So this is made with 20,000 trials. So the variance of this dataset, this formulated dataset, is in reality the population is 1. The population variance is 1. So without the degree of freedom correction, as you can see, we're kind of approaching it, but not really approaching it. Now, just note that this is an average of all of the operations. It's usually not this consistent, of course. But if you repeat the test 20,000 times and take the average, you're going to just get to the population parameters. But if you do it with the degree of freedom correction, as you can see, the green lines, which is the degree of freedom calculations, align with the true population variance, which is 1. So this is why we use the degree of freedom. And that's the only reason. So it's the same as calculating the population variance for a z-score. The only difference is that we're using degree of freedom instead of just the samples. And then we find the variance of the distribution of means, Ooh, what is this? This accounts for sample size and tells us how much sample means are expected to vary from the true population mean. Now, this standard error basically, when you square it, it becomes the standard error, which is used in the calculations, but we're getting the variance right now. But the reason we are dividing it by the sample is because it would be unfair for us to be just comparing the normal individual data points with sample means, because this is just an individual point, or we have just so much substantially less data that it wouldn't make sense for us to compare it with the true population distribution. Does it make sense? I guess it would. Just know that when we are dealing with samples, we don't just take the normal standard deviation or the standard variance. We convert it to the distribution of means, or the variance of the distribution of means, which is just the variance divided by our sample size. And then, of course, we find the standard error. From here on out, it's almost the same as using just the normal z-score. Standard deviation of this distribution of means, which serves as the denominator in your final calculation. It represents the average amount of error we expect between the sample mean and the population mean just by chance. Well, it's essentially the same logic as the individual scores, just you kind of zoom out a little bit and then start treating the sample scores or the sample means as individual scores in the universe that we have constructed. So it's basically the same thing. It's just that it's an error because it's different from what we would get if we just took the population parameters. We calculate the t-score, of course, and how we do that is we take the sample mean, which we calculated in the first step, and then we take our population mean, which was given to us in the formula, or is going to be 0 for dependent test, and then we divide them by the standard error, because we are working with samples instead of, instead of individuals. Yes. So, and then we get our t-test, or the t-value. Let's look and try to see if we have anything that I missed. All of this is just explaining the same things. You can read through them on your own. Let's look at some specifics of the t-distribution. It's used when population variance is estimated. It's bell-shaped, symmetric, and unimodal, just like a normal distribution. There's nothing different about it there. However, it has heavier tails because extreme values are more likely because you don't have enough data. Larger test statistic needed for significance. Now, the larger test statistic needed for significance is not really your concern because it's all listed in a t-table, so it's not really too important for you to know this, but just know it for the exam. Effects of degrees of freedom. As the f increases, t-distribution approaches a normal curve, which we saw at the start. You know it already. Calculating the t-score and hypothesis testing. Of course, we know of the main hypothesis testing rule. The only thing that is different here is, as we know, the z-scores are a set amount of scores. You know, if you get a z of 1, it is 1.64 or something like that. I don't really remember. But if you want a 5% probability here, you must look for your degree of freedom in a t-table. It doesn't have a standard value for each result. it all depends on what kind of degree of freedom you have. And the closer that you get to 30, or the 30 plus, the better it is. The more aligned it is with standard z-score calculations. I wish I put like a t-score table here. It shouldn't be an issue. But just know that the t-table is an important thing to know. So, looking at the t-test for dependent means. Now, until now, we have always had a single sample to go off of, and our universe sample. So, it's usually used in before and after treatments, pre-test versus post-test, before versus after therapy. The counter to this is the independent means test, which we will get to in the next week's video. But dependent means basically means before-after calculations. It's an essential tool for research where two related scores are obtained. How do we do it? The only difference here is that you take the difference of two values. Like you calculate a d-score, which is the difference score for each person. Now, this is participant A, this is participant B. What the fuck? I mean, who creates this? Anyway, it seems our table is flipped a little bit. Normally, the rows are supposed to be participants, and the columns are supposed to be the variables, but it's okay. So as you can see, we have participant A. Before they were scoring 5, but after they scored a 9. Participant B, before they had an 8, after they had a 12. And it goes on and on. So we create a different score for each person. 5, 8, 4, etc. Yes, this is the different scores. You take after minus before, or before minus after, whichever one would make the most sense for your study. It's just that you need to take the difference. And we take a difference in mathematics by subtracting things. So under the null hypothesis, yes. So for actual hypothesis testing, of course, we need a population parameter, or an expected result. The null hypothesis for this one is 0, because we are going to be comparing the different scores to something. And that something is going to be 0, because the hypothesis always assumes the most boring, most normal thing ever. And the hypothesis, or the null hypothesis, is saying, well, if you run this test twice, one before, one after treatment, one before the test, one after the test, etc., you're going to have no difference at all. Therefore, when you subtract the after from the before, you're going to get 0 difference. Okay? So this is why we set the population mean as 0. The only difference from normal calculation is, or the previous calculation that we did, is the fact that we take the different scores and then we create a new data set based off of those different scores. So let's take a look at this here. The null hypothesis is 0. The research hypothesis says that there is a change. And then we calculate the different scores. Couples, these are like, 100 couples, let's say. Or no, there's 19 couples in the study. We take the before, we take the after, we subtract the before from the after, and then we see that there was a 11-point decline. And then we look at the variance. We calculated using the scores that we got from the differences. Look, this result area here is just going to be your new data set. There's no difference there. Like, this difference score is basically just a standardization of these two scores. You just have the metadata of the before and the after values, and then you've essentially squeezed them into a new data set. Makes sense? Maybe. I don't know. I don't hear you. So we estimate the variability, we calculate the standard error. SD2 just means variance. S2 stands for, or S stands for spread, which is variance for our case. And, sorry, standard deviation or standard error for our case. And S2 is basically S squared, which is the variance. And when you put this D down here, it just means the variance of differences divided by the samples and squared, which gives you your standard error. And here we can see the variance score. And then, of course, we have our critical values. Now, one very peculiar thing that you will see here is that, what is this? Am I stupid, guys? No, I'm not stupid. Okay, so this infographic is just fucked. That's why I couldn't really make sense of it. So here we are finding our critical values, our alpha. What score we need to surpass for our result to be deemed significant. So we consult our t-table and we look at our degrees of freedom, and then we find out that our critical value is 2.101 based on our degrees of freedom. And then we calculate the t-value, which is the mean of the different scores minus 0, because as we said, the null hypothesis tells us that there's no difference at all. Nothing ever happens. Therefore, it's 0. So you can just divide the spread of the differences, which is the standard deviation, with MD, which is the mean of the differences. Sorry, the standard error of the differences. And then we get minus 12.05 divided by 2.84. And that apparently equals minus 4, which is amazing result. You can reject any day. So let's look at effect size and power. What is it? Measure the magnitude of an observed difference, not just if it's statistically significant. In a dependent means t-test, you look at it by taking the mean difference and the standard deviation of differences, so our S. And then you get the D in the dependent means t-test. So example, premarital counseling data, MD equals minus 12.05. As we discussed, the spread is 12.39, and the effect size comes out to 0.97. Negative sign shows us that there's a decrease, and an absolute value of 0.97 indicates a very large effect. And what is power? Is the probability of a study detecting a real effect as statistically significant if it exists. We all know about power by now. I don't think we need to know how to report a t-test result in research articles, but just in case, you do df in parentheses, values, p smaller than 0.05. And that's it.